Thanks everyone for coming. Today I'll be talking about privacy in the time of large language models. As I said, it's a small audience, so feel free to interrupt and ask me questions, no problem at all. So my name is Charit Piris, and I'm a research scientist at Amazon Alexa. This is my awesome team. We are the privacy arm of the trustworthy Alexa team within the Alexa NLU organization. And this talk looks at a collection of academic work, some of which have been done by collaborations that include members of this team. You can see there's a cross-section of people from academia as well as industry. And Rahul Gupta, one of my colleagues, is the one who gave the previous talk on fairness in NLU systems. So our team kind of, does a cross-section of this privacy, fairness, and content moderation work. So over the past few years, there has been a steep upward trend of interest in transform-based large language models. Released in 2018, that's just 5 years ago, BERT is a popular large language model that is well known by most of the community. You can see that in the top left-hand corner inside the blue dashed square up there. Another popular one is GPT-3, seen in the red dashed oval. And this is the foundational model behind the famous ChatGPT that's recently hit the news. Now that I've mentioned ChatGPT, I don't think I'll be mentioning it again. But there's been a lot of other models as well that have been released, and this image shows some of them. So you can see that the radii of the circles correlate to the parameter sizes of each of these models, and the companies, the colors represent different companies. So you can see how big and diverse these models have become. As is evidenced from news as well as recent literature, these big models have dominated the deep learning framework, deep learning stage. So the question is why? What has made them so special? So large language models have some solid advantages. First off, they show state-of-the-art performance across multiple tasks. Second, they show utility across a large number of tasks. And also they do really well in situations where they have very few data points to be trained with. These are few-shot and zero-shot settings. And this can be very helpful and exciting for developers handling tasks with low amounts of data. Now, like with most good things, LLMs also have some downsides. One of them is that they tend to memorize portions of their training data. Memorization has been a problem in other machine learning models as well, but in language models, this produces the risk of training data being regurgitated verbatim by the model. So, large language models are trained on crowdsourced corpora, usually, that is difficult to curate because of its sheer size. And this data can include personal data, that is data that can be linked to a specific person, or PII data, or personally identifiable data, that is data that is itself identifying in some format. So in this example, we can see a case where an attacker or some entity can feed a sequence, Jonathan's telephone number is, into an LLM. And the LLM, in this case, outputs information that it has memorized that happens to have PII on Jonathan. So obviously, this is a privacy risk. Now, you might ask, okay, what about personal data? Is it really bad? Is it really identifiable? How bad is it? So here's a factoid to give you a rough idea. A study by Latanya Sweeney found that 87% of the US population can be uniquely identified by using only zip code, gender, and date of birth. So protecting a model from revealing these characteristics becomes a very important case. Okay, so in industrial applications, LLMs usually go through a typical life cycle. Training data is usually used to pre-train a large language model, and this is usually a very compute-intensive task. LLMs can be directly fine-tuned to be task-specific. They can also be distilled into smaller manageable sizes, and these distilled models can be fine-tuned in turn. All of these models can be deployed on device or on the cloud, and more training data can be collected by these deployed models through customer interactions. So within this lifecycle, we can look at what points have privacy risk. So first off, the data feeding into different parts of this lifecycle itself can be a risk. For example, poisoning attacks can be done to insert malicious and misleading data into the models, and that can make them function incorrectly. The models themselves can be at risk in several ways. So for example, malicious entities might choose to do model extraction attacks, where they might use query access to the model to reconstruct a substitute model. Or malicious entities might try to do a data extraction attack, where they try to extract the training data of the model. Also, exposure of private data during open language generation tasks can happen unintentionally without any malicious intervention. And all these things can cause privacy risk. So we've mentioned a few ways that privacy risk can occur, and we've outlined where it can occur in this language model lifecycle. For this talk, we focus on a few types of risk. Most importantly, preventing the risk of customer data from being leaked is of much importance to any voice assistant. So when considering this perspective, risks related to training data leakage from model output become important. So we focus on those in this talk. So the question that we explore here becomes, how do we protect LLMs from training data leakage via exposure during open language generation tasks or data extraction attacks? So we approach the problem in two straightforward stages. First, we talk about privacy measurement. And privacy measurement involves measuring the risk carried by an LLM of being exploited. Here in our case, we explore variants of membership inference attacks that can be used to measure risk. And we also explore suffix matching with the right test sets to enable privacy risk comparison across LLMs. And the next area that we want to talk about is privacy preservation. So privacy preservation involves a set of techniques that can be applied at different stages of the LM lifecycle that I showed you before to mitigate these risks. So in this case, we explore choosing a suitable objective function during pre-training, optimizer-based privacy preservation methods used in pre-training and fine-tuning, and also post-hoc privacy preservation methods that can be used during inference. Note that this is not an exhaustive list of what is in the literature or what we do at Alexa. It might also even be obsolete a little bit because during the last 2 months, there has been a huge amount of research that has come out. But we aim to provide a cross-section of valuable solutions. Okay, so first let's talk about privacy measurement. Let's go back to our LM lifecycle. We have two major artifacts that need privacy consideration, and they are data and models. So the characteristics of the data itself can lead to privacy risk. For example, if several users have a lot more data in the training set than others, their language characteristics might be inferable from model output. Characteristics of the model output itself can lead to privacy risk. For example, if features of the model output can be used to infer if a certain user or sequence exists in the training data, this becomes a privacy risk. Or if the model regurgitates training data, this also becomes a privacy risk. The membership inference attack is a popular data extraction attack where an attacker tries to infer whether a given data point is in the training data set. And we utilize variants of this attack based on work by Song et al. To measure risk in both data and models. So let's first talk about MIA for data audits. So in their work, Song et al. Present a method for training a measurement model that they call an auditor. So in this formulation, the auditor's goal is to learn to distinguish target model output between sequences that it has seen during training. Those are called member data. And sequences that it has not seen during training. Those are called non-member data. So membership here relates to if the data was a member of the training data set that was used to train the target model or not. So we expand on their work to build an MIA data audit. And so here's a schematic of our setup. So first we obtain the training data set of the target model. We sample K train sets and K test sets from this data set. Note that each train set and its corresponding test set is completely independent. We train K shadow models with the same architecture as the target model that we intend to train using the train sets that we sampled. And now we feed the train and the test sets through these models to obtain output features. So the output features from the train set would be member since the model has already seen them during training. And the outputs features from the test set would be non-member because they're independent and the model has not seen them during training. So these output features are paired with their member-non-member labels and used as audit data to train an audit model. And the AUC of this model provides us with a metric of how extractable this data set might be. So as mentioned before, if several users have a lot more data than others in the train set, if the data has identifiable characteristics and poses a privacy risk, this audit will help identify this issue, and data can be processed or resampled in some way to address this issue. Now, there are some drawbacks here. So this method can work for shadow models of a certain size, but for large language models, training K models could be prohibitively expensive. So for comparison, according to Struble et al., the cost of training GPT-2 is about $13,000 to $43,000. So imagine a conversation with your boss asking for resources to train tens of these models for every audit. That is going to be a tough sell. So this method is effective for measuring risk in data, but the shadow models have to be of a limited size. So now let's talk about MIA for model audits. So as with the data audit, we obtain the training data for the model, but we also take a reference data set that is similar in distribution to the training data set, but completely independent, and we call it the non-member set. So instead of shadow models, we use the target model itself to run this data through and obtain features. And the AUC provides us a way with measuring the privacy for the target model. So this method is feasible in terms of the number of models trained, as it essentially trains only one model. In terms of running the audit, using the full trained data set might not be feasible because inference will obviously take some time, and time is value. So sampling the data set on both ends, on the member and the non-member data, would make it feasible. Okay, so thus far we've addressed the question of, given some data, how inferable is its presence in the training data of a given model? Now we ask the question, how extractable is the training data given a model? Or in other words, how much does a model memorize its training data? So in their work in 2022, Kalini et al. Presented a definition of memorization for large language models. And this can be used to simply and efficiently measure and compare privacy across LLMs. So here's a schematic of their process, a simplified schematic of their process. So consider a sequence that is present in the training data. The quick brown fox jumped over the lazy dog. They split it into a prefix of a certain size and a suffix. They pass the prefix into the model and use greedy decoding to get an output. If the output is an exact match to the suffix, they say it's extractable. If it's not extractable. So you can choose a relevant test set of sequences and run them through the model in this way and average the binary values of extractability per sequence to provide a measure of memorization of the model. So this is a nice method to study how different variables might affect memorization and compare across large language models. It's computationally efficient since there's no need to train additional models. Now, in some cases, like when the models get smaller or just have low memorization, you might have low numbers of exact match rates. So you can use a more nuanced version of this metric, which measures the fractional match rate with the ground truth. And this provides a better signal for measuring memorization. Or you can also consider to do a top N output from the model, or consider the top N outputs that the model produces and see whether the ground truth actually appears within them. So this metric is more robust to measuring exposure in cases where multiple outputs of the model are in use, like synthetic data generation use cases, for example. Okay, to summarize, we discussed several methods to measure privacy of LLMs, which were the use of variants of MIA for model and data privacy measurement, and suffix matching for memorization, measurement, and comparison. So the next question is, how can we reduce this risk? This is where privacy preservation comes into the picture, and the next part of the talk is going to be dedicated to that. Okay, so let's go back to our LM lifecycle and first ask the question, what are some places that privacy preservation can be applied here? So privacy preservation techniques can be applied in any of the training phases. So they can be applied in pre-training, distillation, fine-tuning. We can also apply privacy preservation post-training at inference time as well. So the next question is, what privacy preserving techniques can we apply? So for the pre-training phase, the answer can be simple in some cases, like to choose the right pre-training objective. And I'll talk about that in a little bit. We can also apply optimizer-oriented techniques such as differentially private stochastic gradient descent, or DPSGD. And there's also an efficient DPSGD version that we've worked on, which I'll talk about in a bit as well. Also note that we can apply some of these during fine-tuning and distillation stages as well. So let's start with techniques that can be applied during the training phases. Now, Carlini et al. In their work on the GPT-Neo family showed that memorization scales with context size. That is, if an attacker has a longer prefix or more information, they can prompt the model with this, and they will likely be able to extract more information as well. So this is shown in the plot on the left-hand side. So note that the GPT-Neo family of models was trained on only a causal language modeling objective. However, experiments run by our team shows that when mixing a denoising objective into pre-training, the resulting models do not show this, and that's the plot on the right-hand side. We found that adding denoising can serve to limit the privacy risk posed by an attacker with longer contexts or more information. We also found that models created in this way show competitive performance across multiple tasks with much larger models. So this shows that choosing the right objective for pre-training, in this case denoising, might actually help privatize the model without really having much effect on utility. So as we mentioned before, optimizer-oriented techniques such as DPSGD are good tools for achieving the required levels of privacy in LLMs. Any DP algorithm protects the privacy of each example by adding noise. So the DPSGD algo does the same by adding noise to the stochastic gradient descent optimizer. Note that adding noise changes the model in place, and developers can achieve a level of privacy that is kind of stamped onto the model itself. So even if an attacker gets full access to the model, it's theoretically protected. And this is kind of nice. However, DPSGD has its downsides. So in most cases, the accuracy of the models trained with DPSGD remains lower than that of their non-private counterparts. Also, DPSGD clips and processes individual gradients, and this causes significant increase in compute time. So there's about a 20x increase in some cases when using DPSGD versus not, and this is pretty expensive. So we introduced a DP training framework called Efficient DPSGD that addressed some of the runtime concerns of this setup. So as with any DP algorithm, our method also adds noise to ensure privacy. However, we improve on plain DPSGD where the following. We apply microbatch computations per GPU, which is much more efficient. We also add noise scaling and noise decay that allows the addition of noise in a more nuanced and efficient way across layers and iterations. And so this allows the achievement of a level of privacy that is stamped onto the model itself, just like before, but it's not as costly as DPSGD, both in terms of time and in terms of money. Okay, so we discussed some techniques that work during the model training phases. While the privacy aspect of this approach is secure, the approach has its downsides. One, it's costly. Even the efficient DPSGD version is about 2x times longer in terms of training time. And also, second, if some update or feedback needs to be applied post-training, some form of retraining of this large language model is required. And this becomes a problem when feedback on the model needs to be implemented in a quick and cost-effective way. So how can we address this? One way to do this is to apply privacy mitigation at inference time. So we now go through a couple of simple techniques that we use for improving privacy preservation that can be applied during inference. Now, remember that DPSGD methods add noise during training. We can change this and instead add noise to the output during decoding so as to obtain a privacy guarantee. So in our paper by Majmouda et al., we do this with our DP decoding technique. So this noise addition is shown in the paper by using a toy example of a two-dimensional probability simplex that is the triangle shown here, but it can be summarized as an addition of noise to the probability distribution of the output. So consider this. The model outputs a probability distribution for each token given by Q, which is the best in terms of utility. On the other hand, a uniform distribution across the vocab would be the best in terms of privacy, but the worst in terms of utility, obviously. And this can be considered as noise. And so for each masked token, this method obtains a noised distribution Q dash by linear interpolation between the original distribution Q and the uniform distribution U. So using this simple method, a defender can, at runtime, apply privacy without retraining the model. And privacy utility can be adjusted as required during this interpolation process. So in some cases, though, noising the right PII span instead of the whole utterance might be of value. And this can be achieved by a simple detect and filter strategy where we treat PII detection as a slot tagging problem. Now, slot tagging is a common task in the context of voice assistants. So these models are actually readily available for us. We can retain these models or retrain these models to detect a subset of the slots they are trained to identify, which we have identified as PII. So here's an example. Assume a sequence produced by an LLM. Jonathan's telephone number is 12345678990. We can pass this through a slot tagging model that is trained to detect phone numbers, and it'll label the phone number. Once the span is detected, it becomes a simple filtration process, and we can filter, redact, or obfuscate using a mapping function or a trained model. Now, this simple method does not require training the original foundational model. Privacy utility can be adjusted based on what's raised as PII by the detector and how that's handled. So that's pretty straightforward. However, there are some challenges that need to be mentioned here. First off, not all PII-like spans are PIIs. So, for example, when considering the sequence, Lionel Messi is the captain of the Argentina football team. Lionel Messi is a celebrity, so this sequence is not really high in terms of privacy risk. However, when considering the sequence, Charit Pires is the captain of the Arlington Cowboys senior football team. Charit Pires is a lesser known entity, and this sequence might actually be providing some information which is of value to some malicious entity. So the difference in this is very difficult to figure out. Also, if we take a sequence like, I am the principal scientist in the startup X123 that consists of 5 people. Now, this sequence doesn't have any PII, but it is personal in nature, and someone might likely identify who this sequence belongs to. And detecting such sequences has proved to be very difficult. So we need to leverage better context recognition in order to better identify PII and personal data, and this research is in progress. So, in conclusion, we've discussed privacy measurement and privacy preservation techniques for LLMs. In terms of privacy measurement, we note that variants of MIA can be used to measure risk in models and data. It's costly, but it's effective. Suffix matching with the right test sets enables comparison of risk across LLMs. It's cost effective and also easy to use. And in terms of privacy preservation, we note that denoising limits the privacy risk posed by an attacker with longer contexts without any effect on utility. Optimizer-based methods can provide privacy even in the case of an adversary gaining full access to the model. This is effective but costly and causes some utility degradation. And finally, post-training privacy preservation techniques can be applied during inference. And although they don't secure against an attacker with full access, they are cost-effective and easily maintainable, and their privacy utility is tunable without altering the large LLM. So that brings me to the end of my talk, and now I'll take some questions.